Hello there, Mr. Sutton here, bringing you the Algebra 2 4-1 Part 2 homework solutions on graphing polynomial functions. For the first couple problems, we are given a function and we're trying to describe the end behavior of the function. So for all of these, the key thing to do is to pick out the lead term, the term with the highest exponent, and see what that's doing. So in this case, we have this negative 5x to the fourth term, which is a negative x to an even power. This is the key here. Since it's negative, well, let's start with the even odd. Since it's even, this means it's going to be a parabola kind of shape. And since it's negative, it's going to be an upside down parabola like this one. So in terms of end behavior, that means that as x approaches negative infinity, as we go to the far left, our graph is going down to negative infinity. And as x approaches positive infinity, as we move to the right, then the h function is moving, well, still down forever. So we're going down either way. For this problem, trying to figure out the end behavior of this g function, we notice that our highest term, our lead term also, is a positive x to an odd power. So because it's odd, that tells us it's going to be a line sort of shape that starts and ends in opposite directions. And because it's positive, it's going to be an upline kind of shape. So this means that as x approaches negative infinity, as we go to the left, our graph is going to negative infinity. It's going down. So g of x is also approaching negative infinity. As x approaches positive infinity, as we move to the right, well, now we're going up forever. So g of x is approaching positive infinity. For the next 3 or 4 problems, we're being asked to graph this polynomial, or a polynomial, using a table of values. So what we're going to do is we're essentially going to set up a table using the x values -2 through +2. Just plug them all into this function, get some y values, put it on a graph, and then use the end behavior to fill in the rest of the picture. So for this one, let's go to Desmos and set up my function so I can plug these 5 x values into it. So here I am on the Desmos scientific calculator. I'm going to set up my h function here. So h of x equals, let's see, we got 5 plus 3x squared minus x to the fourth. And I could put this in standard form, but I don't really need to if I'm just plugging things into it. So let's plug in some numbers. We've got h of -2 comes out to 1. So let me put that in there. And then we're doing h of -1, which is 7. And then h of 0, I don't really need to plug into the calculator. That's just going to zero out anything with an x. So that's just going to be 5. And then for this next one, let me just plug in 1. I could probably do that without a calculator too, but hey, there is 7. All right. And then we'll plug 2 in. I have a suspicion it's going to be 1. This thing looks kind of symmetrical, but you never know. Let's plug in 2 and see what we get. Yep, it's 1. All right, so let me graph this. I don't need to make my grid lines go super crazy because the highest value I need on this one is 7. So if I go up to 8, for example, that should be sufficient. So we've got -2, comma 1, which is right here. And then -1, comma 7 is all the way up here. 0, 5 is right there. 1, comma 7 is back up here. And then 2, comma 1, that's going to be down here on the lower right. Before I connect the dots, let me also figure out my end behavior. So because my highest exponent term, this lead term, is -x to the fourth, it's -x to an even power. That means this is going to be an upside down parabola type of end behavior. So I'm going to start below the first point and I'm going to end below the last point. So starting down here, going forever in this direction, we're going up through these points, connecting them, and then going down forever this way. To graph this polynomial, let me first make a table using x values from -2 to +2. That'll get us some points, and then we'll use end behavior to get the rest of it. So going to Desmos, because I'm going to plug all these x values into this p function. So let's put the p function in here officially, just to make it easier to plug things in. So that's x to the fifth minus 3x to the third plus 2. And then let me go and plug in -2 to the p function. That gives me -6. And then we'll plug in -1. That'll give me 4. Plugging in 0, don't really need the calculator. That just zeroes out these x's to give me 2. Plugging in 1, that gives me 0. And then plugging in 2, positive 2, that's giving me 10. So in order to graph these, I need to be able to go from -6 to 10. So for my grid lines, I've got a little bit more revealed here. And then let me go do -2 comma -6. So that is right here. And then we've got -1 comma 4 up here. 0 comma 2 is right there. 1 comma 0 is on the x-axis. And then 2 comma 10 all the way up here. For my end behavior, I've got a positive x to the odd power as my highest term, my lead term. So that's going to give me an up line sort of end behavior. So we're going to be starting low and ending high, going to negative infinity as we go left and positive infinity as we go right. So starting down here and just going through and connecting all those dots and ending going up forever. Let's go ahead and graph this polynomial now using a table of values. So let me set up my table from -2 to +2 for the x values. And I'll just go to Desmos, clear some stuff out, and plug all this stuff into the g function, or the f function. Just for accuracy's sake, I'll call this the f function. So we've got f of x equals 4x minus 9 minus x to the third. So let me plug some things into that. So we have f of -2, which comes out to -9. And then let's do -1. That's going to be -12. Plugging in 0 gives me -9 again, which is kind of interesting. Plugging in 1, we've got -6. And then plugging in 2, that's going to give us -9 again. Very interesting. All right, so I need a graph that's going to let me go from -6 to -12. So this is mostly going to be below the x-axis that I'm showing here on my window. So we've got -2 comma -9 down here on my graph. And then -1, -12 is all the way down here. And then we've got 0, -9. 1, -6 is going to be right here, a little higher up. And then back down to 2 comma -9, which is right here. So this almost actually kind of looks like an upside down sine wave for when we get to the trigonometry chapter. That's kind of neat. But what does this look like before and after those final points? So we have a -x to the third power, -x to an odd power is going to be our lead highest term. So that's going to give me a down line sort of end behavior where we are beginning above this last point and we are ending below the final point. So we've got starting up here, going through, connecting some dots, and ending below the final point. In order to graph this h function, let's make a table of values and plug in the x values from -2 to 2. And to plug all these in, I'm just going to use Desmos. I could probably do it without Desmos, but just for accuracy's sake, let's do that. So let me clear out whatever is in there already. And let me define the h function in Desmos. That's going to be x to the fourth minus 2x cubed plus 3x. And let me go down another entry and do h of -2 just to kick things off here. So that comes out to 26. It's kind of a high value for one of these tables. And then we'll do -1. That's coming out to 0, so that's quite the jump. And then plugging in 0, we get 0 again. Very interesting. Plugging in 1 gives us 2. So these are all very small values compared to that first one. And then let's see what happens if I plug in 2. That's coming out to 6. All right, so my grid lines need to accommodate this weird 26 one. So I'm going to make my grid lines go by 10s, at least the major grid lines. I've got some minor going by 2s grid lines as well. So we've got -2 comma 26 is all the way up here. And then we have -1, 0 right on the x-axis. 0, 0 also on the x-axis. I'm probably going to have to go down below. I would need to graph more points to be super accurate, but we'll just go with what we've got here. Then we've got 1 comma 2, which is right here. And then 2 comma 6 is up here. So for my end behavior, we have a lead term of x to the fourth. That's a positive x to an even power. That's going to give me an up parabola sort of end behavior, which means I'm going to be starting high, and I'm also going to be ending above that final point. So let me start up here, go down through these other points, and then we'll end on a high note here. For this problem, which has multiple parts, they're telling us that the estimated population of Sumatran tigers can be modeled by this P of t function, where the t is just the number of years after 2000. So they want us to use technology, aka Desmos, to graph this function from 1 to 18 on the t-axis, and then describe the behavior on the interval. And what they're saying by this is basically, where is this thing increasing, where is it decreasing? So firstly, we have to graph this on Desmos. Let me go to Desmos and do that, and let me just move this down so I can see my function here. So I'll start by putting my P of t function in Desmos. So this is negative 0.077 t cubed, and then we have a plus 2.11 t squared. No way I could do this without technology. Minus 7.1 t plus 166. All right, so let's see what this graph looks like. It doesn't look like much of anything. So the reason is that there's probably not like only 8 or 9 Sumatran tigers in all of existence. We probably need to adjust our window a bit. On the t-axis or x-axis, they said we were going from 1 to 18. So let's go from negative 1 to 20 so I can at least get the correct input values in there. I don't really need any negative values. For the y-axis, I think we're a little bit low. Let's see what happens if we multiply that by 10 and make 80 kind of the top value. Well, I still can't really see much of anything. So let me go again, and let me multiply by 10 again and make this 800 for the upper value. Now we're seeing something. And if I really wanted to, I could just make the top value maybe like 400, and now we've got a pretty good picture of what's going on. So when you're doing this whole increasing decreasing thing, it's nice to use these minimum and maximum sort of predefined points that Desmos has built in. If you just click on these little gray dots, then it'll hold those in place so that you can keep referring back to them. So let me just do increasing intervals first. It looks like this function is increasing from roughly 2 to 16. So here's our graph. So from 2002 to 2016 would be our increasing interval. That's a lot of time the Sumatran tigers are happily growing as a population. But then we had some other times, for example, between 2001 and 2002, and also after 2016 to 2018, where they were declining. For this next problem, also on this honors problem here, they're asking for the average rate of change in the number of tigers from 2001 to 2018. So they're basically asking for the slope if you plug in 1 and 18. So our rate of change formula, we're going to do P of 18 minus P of 1. That's essentially y2 minus y1 over 18 minus 1. That's x2 minus x1. So just using two different points that are on this graph and finding the slope between them. So let me go back to Desmos and actually plug some of this in. I've already defined my P of t function, which is kind of nice. So I can just do, let me make a fraction, and let me just do P of 18 minus P of 1. And I could calculate those separately or just not. Let me do 18 minus 1 down here, and this all comes out to 6.579. Now, if you calculated these individually, it would be like 272.776 and 160.933, but again, it would come out to 6.579 tigers per year would be our units on this one. For the final question on this, they're asking if we think this model can be used for years after 2018 and explain our reasoning. So you could look at the graph and start, checking out what's happening to this as you keep going forward in time, and at some point you'll notice that it's going down into negative territory, which doesn't seem very realistic if we're talking about the number of tigers. I mean, sure, you could have 0 tigers if they all die off, but I mean, what is a negative tiger, right? So the issue here is because this is a negative odd function, the p of t function is going to be going to negative infinity as t goes to positive infinity. This thing goes down forever because it's a polynomial of this nature here. So for that reason, this is not a realistic model for all that long after 2018.